A little bit of homework last night, page 523, number 7 to 10. Any issues with any of those 4 questions, 7 to 10? 10C, okay. 10B, you say? 10A? Oh, let's just do 10. Let's just do all of it, okay? Any others besides number 10? 9? 9A and B? All right, let's do 9 then. Okay, let's take a look at number 9 first. Number 9 says, compare the distribution of charge on hanging aluminum and glass rods if both are touched at one end by a negatively charged ebonite rod. Aluminum and glass. What's the difference there between aluminum and glass? Yeah, aluminum is a way better conductor than glass is, right? Glass is a pretty good insulator. Aluminum is a very good conductor. Well, let's draw out the aluminum. We'll make aluminum blue, and we'll make our glass rod green. Now, both, doesn't say whether they're neutral or whatever. Let's just assume they're neutral, see where that takes us. And we're going to bring a negatively charged ebonite rod nearby, and we're going to touch it. So here's our ebonite rod. Our ebonite rod is red, and we're going to touch it. What's going to happen there? Are we going to get a transfer of negative charge in either or both of these? Yes? Yes. The reality is you're going to get some transfer of negative charge in both cases. Okay, you're going to get the glass rod becoming somewhat negative as well. Some of the electrons will go over there, but you're going to get a lot more transfer of charge in the aluminum. And why are you going to get a lot more transfer of charge in the aluminum? Pardon me? Because it's a conductor. Now, the reality is, as it's touching, what does it want to do? Yeah, they want to balance out, right? Are they going to balance out? Well, they're more likely to balance out here than they are down here. Okay, but the goal is, in both cases, to balance out. So they're both going to become negative, just that you're going to find the aluminum is going to become more negative, probably, than the glass rod. Make sense? Anybody say something more or less like that? Yes, it would. Yeah, that's a good point. Yeah, very good point. Rucker said, would the glass get charged a little bit more near the point of contact and a little bit less throughout? Yeah, it would, because the electrons aren't as free to move about. You're going to get some electrons still transferring from the ebonite to the glass, but they're going to have a harder time distributing throughout it. So you are going to have a little bit higher concentration of electrons over here near the contact point. Yeah, absolutely. Good point. Let's take a look at B here now. After a small negatively charged metal sphere momentarily touches a larger neutral metal sphere. Oh, this one should have almost been A, because this one's easier, right? B's easier. You got a small negatively charged sphere. Let's say 4 positives, 4 negatives. It touches a larger neutral sphere. Oh, wait, that was negative, wasn't it? And we got a larger neutral sphere. 5 positives, 5 negatives, whatever. What's going to happen? Well, when negative touches when negative touches neutral, they're going to try to balance out, right? Are they going to balance out in this case? Well, they're kind of telling us no, they're not going to balance out, because we're saying one is a small one, one's a big one. Remember what I said the day we learned this? The goal is to balance out, but if you have different size, different shapes, different materials, then they're not necessarily going to balance out. They're clearly telling us here that, look, one's a lot bigger than the other one. They're probably not going to balance out, but we are still going to get electrons moving over this way. So they are both going to become negatively charged, but they're not going to balance out. This guy The reality is this guy over here is going to accept a lot more electrons than this guy can give, or sorry, than this guy will take. So it's easier for this guy to have more electrons or a bigger negative charge than this one. Does that make sense? So they're not going to balance out equal, but we are still always going to get that transfer of charge taking place, even to some degree when we've got insulators here. We got conductors here. We're going to get a pretty big transfer of charge, but they're not going to balance out. Right? Big objects can hold more charge than little objects. All right, our last question was number 10. It says a negatively charged ebonite rod is held near the knob of a neutral electroscope. So let's draw the electroscope here right now. Okay, there's our electroscope. There's the metal rod on the electroscope. There's the little ball on the top of the electroscope, or the knob of the electroscope. And there's the two leaves that are not separated right now. When we bring a negatively charged ebonite rod nearby, let's draw some positives and negatives in here, actually. Looks like this electroscope is neutral, right? In fact, all parts of it are neutral. When we bring the negatively charged ebonite rod nearby, what's going to happen? Well, what's going to happen to the protons, first of all? What's going to happen to the protons, Jazzy, in this neutral electroscope? Good, the protons are going to stay where they are. What's going to happen to the electrons? Janessa, what's going to happen to the electrons in this neutral electroscope? Good. They're going to be pushed away as far as they can, right? So let's erase these electrons here. And let's say that those three electrons that were kind of beside the positives get pushed down here. Now the leaves are both negatively charged. What happens to those leaves as a result of them both being negatively charged? They're going to separate. They're going to repel each other, right? B says, explain what happens to the leaves of the electroscope if the other side of the knob is now grounded while the rod is still in place. It doesn't really matter whether it's the other side or the same side. The bottom line is it's being grounded. So let's attach the ground wire here. What's going to happen? Well, we're not going to suck electrons up from the ground, right? Because the whole thing causing this is a negatively charged rod. So you're not going to pull electrons toward a negatively charged rod. Rather, you're going to push electrons down. So these electrons get pushed away from even the leaves of the electroscope down through here, down into the ground. These leaves still separate, but now they're separated not because they're negatively charged leaves, but because they're positively charged leaves. Still like charges, though. And C says, explain why removing the ground first and then the rod will leave a net charge on the electroscope. In other words, the leaves of the electroscope will stay spread apart. If you've got, if you take away this grounding wire before you take away this. Why? Don't the electrons want to redistribute and make it neutral again, John? The grounding wire, they can't go back and redistribute, right? Because the electrons, or at least a preponderance of the electrons, have been driven down into the ground. Now they can't come back up. They'd like to come back up, but they can't come back up because there's no path for them to go up. Make sense? You guys might remember in Physics 20, we talked about a law called Newton's law of universal gravitation. It essentially said that when you got two objects with mass, there will be a gravitational force of attraction towards each other. Object A will pull object B will pull object A. Now, that gravitational force of attraction, although we typically think of gravity as being a pretty big force, it's actually not. Gravity is actually a pretty small force in the grand scheme of things. The only reason we think of it as being a big force is because our experience of gravity involves the Earth, and the Earth is massive. So because of that, that force is a pretty measurable force. But if you're dealing with two masses like you know, two masses that are 50, 60, 70, 80 kilograms, the gravitational force of attraction between those two masses is minuscule, immeasurable. There is a force of gravity there, but it's ridiculously small. Now, there's another force that acts in a real similar way to the force of gravity. It's called an electric force. That electric force is a bigger force. It's a larger force, all other things being equal. the electric force is a bigger force. It's real similar to the gravitational force, other than in magnitude. It's real similar in a lot of ways, including an experiment that was performed in order to derive this experiment, or to derive this law. If you remember in Physics 20, we would have talked about an experiment called the Cavendish torsion balance experiment. That was an experiment that was performed by a guy named Cavendish to find the gravitational constant, that big G that has a value of 6.67 times 10 to the minus 11. It's not what discovered the law, but it is what discovered the value of the gravitational constant. A similar experiment was performed by Charles Augustin de Coulomb, the guy who the unit for electric charge is named after, Coulomb, in order to derive the law for electric force. Here's basically how it went. Now, what I'm about to show you is a bit of a simplification, but that's okay. Okay, it's enough detail that you need to know. Basically, it works like this. You got a fixed surface. Maybe it's the roof, maybe it's a ceiling, maybe it's the top of a box. It doesn't really matter. It's a fixed surface. And hanging from that fixed surface is a string. And on the end of that string is a rod. And on the end of that rod, on either end, there's a little ball. One of those balls, at least, is charged. We're going to call that charge 1. The other one, I don't even care if it's charged. It's got to be equal mass so that literally this thing doesn't tip over, so that it's balanced out, but it doesn't have to be charged. We're going to bring another charge nearby, charge 2, that's represented by my fist, we're going to bring nearby. So my fist right now is coming nearby charge 1. Charge 2 is coming nearby charge 1. See the shadow of my fist coming by it on the screen there. What happens to charge 1 as a result of my fist coming near it, or as a result of charge 2 coming near it? One of two things can happen. What's one of them? They can be attracted to each other. So charge 1 can be pulled towards charge 2, or alternatively, charge 1 could be repelled. It could be pushed away from charge 2. Depends upon what the signs of charge 1 and charge 2 are, right? Both positive, both negative, one positive, one negative. Doesn't really matter. Bottom line is there's a deflection. There's going to be a deflection of charge 1. It's going to move as a result. Now, it might not move very much, but it's going to move as a result of charge 2 coming nearby. So how does that help us? How does that help us to determine a law that describes the force between those two charges? Well, let's look at a couple other things that we need to measure first. Let's measure the value of R. R is the distance that separates charge 1 and charge 2. We can measure the value of R real easily. Right? We can use a ruler or some kind of measuring device like a ruler in order to determine how far charge 1 and charge 2 are apart from each other. Why we don't call that D, the distance they are apart, I'm not sure, but we call it R. Okay, regardless of whether we like it or not, that's what we got to call it. We can measure that value easily. Now, the values of Q1 and Q2, we can't, or we could, but Charles Augustin de Coulomb couldn't measure the values of Q1 and Q2 directly. He had no device for saying, oh, it's got this much charge, this many coulombs of charge. We didn't even have that unit for charge at that point. But he was able to measure the relative values of the charge. And in the end, for this experiment, that's all he needed. He didn't need to know the value of the charge. He just needed to know if this charge was doubled or tripled or quadrupled. So how do you do that? Basically, he'd take whatever one he wanted to manipulate the value of the charge for, either charge 1 or charge 2, and then he'd keep touching it against neutral objects. If charge 1 has a value of Q, and I touch it to something that's neutral, then it has a value of charge that is 1/2 Q. Right? They both balance out to be a 1/2 Q. If charge 1 is a 1/2 Q, and I touch it with something that's neutral, then charge 1 becomes a 1/4 Q. And then if I touch it against something that's neutral again, it becomes an 1/8 Q. So I can actually manipulate the value of Q1, or of Q2 for that matter, by repeatedly touching them against something that's neutral, and then, again, not determine the exact value of the charge, but to determine the relative value of the charge, what it is now compared to what it was before. So again, we're not getting a number for Q1 and Q2, or at least Coulomb wasn't, but we can determine what amounts to a value, relative value. Now, the only other thing that we want to measure here, this is the tricky one, F, the force. force of attraction or repulsion. We can't just take a Newton scale, a spring scale, or something like that, and measure the force of attraction acting on charge 1. Here's what we do. We do something, believe it or not, similar to what you've done when you were 5 years old on the playground. You go to the playground, you're 5 years old, you run to the swing set. Everybody likes the swing set. Go as high as you can. Everybody thinks, oh, I'm going to go right over top, circle right around. You guys know in Physics 20 that you'd have to be going really, really fast to do that in order to go the minimum speed necessary to go over top. Okay, when your parents tell you that they used to do that when they were kids, they're probably lying. Okay, they probably didn't do that when they were kids. One of the other things that you do, though, with the swing set is twist it up, right? You get on the swing, and then you twist it. You twist it as far as you possibly can, and then you let it go, and then you spin around really, really fast, right? When you twist it up, you know, even at 5 years old, you know that when you twist it up, the more you twist it, the more force is required, right? The more effort is required to twist it up. The more revolutions or the more rotations it's twisted around, the more effort is required. Well, we could, if we wanted to, measure the force that was required to twist it a quarter of a revolution, or a half a revolution, or a full revolution, or 2 full revolutions. We could know, based on how much the swing set was twisted, how much force was required to do that. Then we could turn around and say, oh, he's got it twisted 3.5 turns. It must have required this much force. That's similar to what Coulomb would have done here. He would have done experiments to determine how much force was required to twist this string a certain amount, a certain number of degrees. And then he would have looked at it after this experiment and said, oh, the string twisted 17 degrees, it must have required this much force. Or it twisted 37 degrees, it must have required this much force. He was able to determine the value of the force by the torsional properties, or the twisting properties of the string. All right? So now he's got F, Q1, Q2, and he's got the value of R that separates them. Now he performs 3 experiments, 3 basic experiments. In the first experiment, he's going to manipulate the value of Q1. The responding variable will be the force. So he's going to see how the force of attraction or repulsion responds to the value of Q1. The control variables, what do we got to keep the same here? Well, we better keep Q2 the same, because we can only change one thing, right? Let's keep Q2 the same, and, sorry, let's keep Q2 the same, yeah, and let's keep R the same. So he does this experiment where he manipulates Q1, sees how F responds to it, keeps Q2 and R the same, plots a graph. The graph would be F versus Q1, because it's always responding versus manipulated variable. The graph that he gets there is a straight line. That tells him that the force of attraction or repulsion is directly related to Q1. In other words, as Q1 doubles, F doubles. As Q1 gets cut in half, F gets cut in half. As Q1 quadruples, F quadruples. He's just found the relationship between F and Q1. It's a linear relationship. As one increases, the other increases by the same amount. But then he does another experiment. This time he's going to manipulate Q2. The responding variable will still be F, the force that changes because of Q2. The control variables this time, the things that we got to keep the same, are going to be Q1 and R. Can't change Q1. Did that in the last experiment. Can't change R because we're changing Q2. Plots a graph this time of F versus Q2. Also gets a straight line. That tells him that the force of attraction or repulsion is directly related to Q2 as well. Q2 has the same effect as Q1 does. As it increases, F increases linearly. As it decreases, F decreases linearly. Finally, he manipulates the value of R to see what effect R has on F. The control variables in this case would be what? Charge, both charges, right? Q1 and Q2. Already found out what Q1 does. It's a linear. Q2, linear. Don't need to check those. Can only check one thing at a time. We're checking R, so let's keep Q1 and Q2 the same. Plot a graph of F versus R. This time we get a graph that looks like this. The relationship here is not F is related to R. As R goes up, F does not go up. In fact, as R goes up, F goes down. Turns out to be what we call an inverse square relationship. F is related to the inverse of the square of the distance that separates them. Get enough data, we'd find this. Now Coulomb looks at all three of these experiments, tries to put them all together and says, wait, if F is related to the magnitude of the force is related to Q1, then it's going to be equal to, in part, equal to Q1. Well, it's directly related to Q2 as well. Well, it's inverse related to R squared. You ever done these proportionalities in math class before? If F is related to something, it doesn't mean it's equal to something. F is not equal to Q2. F is related to Q2. So to make it equal, you have to put a little constant out in front. Sometimes I call it a fudge factor. Right? It's related to Q1, Q2 over R squared, but to make it equal to it, we got to stick a little constant out in front. A fudge factor out in front to make it equal. So here's his equation that he derives. It's called Coulomb's law. F is equal to K Q1 Q2 over R squared. The force of attraction or repulsion between two charges is equal to a constant times charge 1, the magnitude of charge 1, not the sign, but the magnitude, charge 1, times the magnitude of charge 2 divided by the distance in meters squared. Does this equation look a little bit familiar to you? Does it ring a bell somewhere, Brad? Yeah, the gravity equation that we were talking about at the beginning of this, right? The experiment that Cavendish performed, Newton's law of universal gravitation. F is equal to G m1 m2 over R squared. The force of gravity is related to the product of masses and the inverse of the square of the distances. While the force of electricity, attraction or repulsion, is equal to a constant times the product of the charges divided by the distance squared. So it is real similar. Same structure of the equation, lots of similarities. A couple differences as well, and we'll talk about those in a bit. Yeah. Coulomb's law says what I just wrote down. The magnitude of the electric force that acts between two objects, positive, 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 negative, 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 is equal to K times Q1 times Q2 over R squared. K is a constant. Now that constant has a value of 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. As opposed to that gravity constant, if you remember that from physics 20, which was 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The equation looks almost the same with a couple different variables. They both have a constant in it. But notice the constant for the electric force is much, much, much bigger, about 10 to the 20 times bigger than the equation for the force of gravity. That becomes important for us in a minute. Before we do some math on this, let's just compare the forces in a couple of different aspects here. Coulomb's law, Newton's gravitational law. Coulomb's law, right? F is equal to K Q1 Q2 over R squared. And Newton's gravitation, which says F is equal to G m1 m2 over R squared. Well, the relationship in both cases is what we call an inverse square relationship. In other words, if R increases, F decreases by a factor of R squared. So it's inversely related to the square of the distance. Now, the magnitude, how big is the force? All other things being equal, we talked about this near the beginning of the day here today. All other things being equal, the electric force will be bigger than the force of gravity. Gravity is a very small force. We think of it as being big, but it's only big because we think of it in the context of us on Earth. And the reason that's big is because the Earth is so massive. If the Earth wasn't so massive, we wouldn't think gravity was such a big force anymore. When we take two small objects that are charged, you take a balloon, you rub it against your hair, and then you put the balloon near the wall. you notice that electric force of attraction, right? It's significant. Do you notice the gravity force of attraction between the balloon and the wall? Not even close, right? What's a bigger force? The electric force. Clearly, we notice that more. We just don't think of it as being bigger. Why is it bigger? Well, look at the constant. It's 10 to the 9 versus the gravitational constant, which is 10 to the minus 11. And the other difference between Coulomb's law and the gravitational law, well, gravity is always attractive. Can't be repulsive. And Coulomb's law is attractive or repulsive. Depends upon what kind of charge you have. Look, you can only have one kind of mass, right? Positive mass. Therefore, the force of gravity has to be attractive. But with charges, you can have either one, positive or negative. So that results in having two possibilities for forces, attractive or repulsive. Let's take a look before we leave here at one example. It's 10.1 on page 530. Here we are 3 days into the unit, our first mathematical example of the unit. A small metal sphere with a negative charge of 2.1 times 10 to the minus 6. I'm going to circle that because I'll probably forget and make it a positive charge if I don't circle it. Is brought near an identical sphere with a positive charge. So we get a negative and a positive, two opposite charges. 1.5 times 10 to the minus 6. The distance between them is 3.3 centimeters. We know we want to convert that to meters. What's the magnitude and the type, attraction or repulsion, of the force of one charge on the other? Now, we can find the force of A on B or B on A. It's the same force. And for both of them, it's either going to be attractive or it's going to be repulsive. What do we got here? We're going to make this Q1. We're going to make this Q2. What if one of you looked at this and said the other way around? What if one of you said this is Q2 and this is Q1? Would it matter? Cole, what's 1 times 2? What's 2 times 1? So it doesn't matter what order you multiply them in, right? If we take Q1 as 2.1 and Q2 as 1.5, and say 2.1 times 1.5, or we do it the other way around and say 1.5 times 2.1, it's the same thing, right? So it doesn't matter which one is Q1 and which one is Q2. One of them Q1, one of them is Q2. This is the value of R. The distance that separates them. We want to find the value of the force. Now, when we use this equation, we're always going to use it to find the magnitude of the force, not the direction. And pay really close attention here. I don't want you to ever plug a sign for charge into an equation. We got a positive charge, we get a negative charge. That's important, but not in the equation. For us, in an equation, positive means direction. Negative means direction. It doesn't mean a type of charge. Okay, I don't want to start doing two different sign conventions in equations. Positive and negative mean direction, not a type of charge. Now, later on, okay, again, it's important that one's positive, one's negative. We'll deal with that later on. K is 8.99 times 10 to the 9, as we said just a minute ago. Q1 is 2.10 times 10 to the minus 6. Now, they give it to us in coulombs, but be prepared. A lot of times you see a question like this, it's not in coulombs, it's in microcoulombs. So we got to be prepared to convert that to coulombs. The other one is 1.5 times 10 to the minus 6, and the distance that separates them is 0.0330, or 3.3 times 10 to the minus 2 meters. So let's say on our calculators 8.99 times 10 to the 9 times 2.1. Again, we're dropping the negative signs here. Times 10 to the minus 6 times 1.5 times 10 to the minus 6. Let's press equals. Let's not try to do too much at once on our calculator. Let's press equals, and then let's divide that by 0.0330 squared. We get a value of 26 newtons. Should be 26.0 newtons, I guess, 3 digits. Now, is it attractive or repulsive? How do we know that? There's a quick answer to this. Parker, what is it? How do you know? Good. That's when it becomes important that one is negative and one is positive. They're opposite charges. Doesn't matter whether they're equal and opposite or not. They're opposite charges. Therefore, it's got to be an attractive force. So we're not using the positive and negative charges until it comes time to determine what direction the force is, what type of force it is, attractive or repulsive. We never, ever, ever plug the sign of a charge into an equation, this equation or any other equation, right? Your homework for tonight are the questions that go along with that on page 530. Only one of them, I guess, hey? Good deal tonight. One question for homework.